Hello everyone. Thanks for joining today's DVCon session. Today we will be discussing about recipe for bugs hunting, tips and tricks for low power silicon sign off. This paperwork has been done by myself, Dipankar, Narendra, Arya, Anuroop and Deepmala Sachan. Taking a quick look at the agenda, first we will be going through some introduction, then basic concepts of UPF, followed by challenges for low power verification at SOC level, and further by conclusion and future research. So, as we all know, power density on system on chip is increasing with every new process node and due to shrinking geometries and an increase in design frequencies. Every new generation of SoCs is adding more and more features and demanding more performance that needs to be met under aggressive schedules to remain competitive in the ever changing consumer technology market. Enabling early capture of power intent is therefore critical for complex low power SoCs. UPF Unified Power Format accomplishes this by allowing the specification of what was traditionally physical implementation based power information early in the design process at the RTL level. It is based on a tickle script and provides concepts and commands which are necessary to describe the power management requirement for IPs or complete SoCs. The figure besides here shows the UPF supporting the design flow from top to down. UPF provides a consistent format to the specified power design information that may not be easily specificable in an HDL. As indicated in the figure, UPF files are part of the design source and when combined with HDL represent a complete design description. HDL describing the logical intent and UPF describing the power intent. This collection of source files is the input to several tools, for example, simulation tools, synthesis tools, formal verification tools. Simulation tools can read the HDL UPF design input files and perform RTL power aware simulation. Synthesis tools can read the HDL input design files and produce a netlist. The tool or user may produce a new UPF file set that combined with the netlist represents a further defined version of the same design. Place and out tools read both the netlist and the UPF files and produce a physical netlist, potentially including an output file. So, with this advancement in the technology, low power designs and its verification is becoming more and more complex. Today's chips have multiple power domains, each having multiple operating power modes and dynamically changing voltage levels. UPF based low power verification is therefore now industry standard and mandatory part in the design verification and implementation flow. IEEE standard UPF allows designer to specify the power intent of the design. A power intent specification in UPF is used throughout the design flow. However, it may be refined at various steps in the design cycle. Some of the important concepts and terminology used in the power intent specification are the following. First, power domain. It's a collection of HDL module instances or library cells that are treated as a group for power management purposes. The instances of a power domain typically but do not always share a power supply set and typically are all in the same power state at a given time. This group of instances is referred to as extent of the power domain. Isolation cell, an instance that passes logic values during normal mode of operation and clamps its output to some specified logic value when control signal is asserted. It is required when the driving logic supply is switched off while the receiving logic supply is still on. Level shifter, an instance that translates signal values from an input voltage swing to a different output voltage swing. It can be either from low to high or high to low. Retention, enhanced functionality associated with selected sequential elements or a memory such that memory values can be preserved during the power down state of the primary supplies. PSTs or power state tables. PSTs define the supply crossing relationship between each supply net in the design as defined by UPF specification. PSTs are the golden reference for low power static verification tools. Okay, so now let's discuss about the challenges which we faced while doing the low power verification at SOC level. In this paper, we have listed about 5 to 6 challenges. Further moving ahead, we will discuss each one of them one by one in detail. First is consideration of low power isolation specifications as constraints to the static verification. Low power specification can be subject to error in translation and interpretation. One such area of concern involves isolation enable, their senses, and their relationship to the power supplies and PST states. So while putting isolation cells when going from off to on domain, we can consider the following design constraints. For example, if isolation enable E1 is related to supply I1, then we can make the constraints like first, if isolation enable E1 is active or it is clamping, then I1 is guaranteed to be off. If isolation enable E1 is inactive, then or transparent, then I1 is guaranteed to be on. So with these design constraint information, we can statically catch issues where an isolation is allowing the corrupt data to pass from off to on domain or blocking the valid data from on to on domain based on the given PST combination. So if we see the state tables here, we can check each of the errors one by one. For example, the first one has the allow error reflected in red. So here the isolation enable is going from off to on domain, but it is allowing the corrupt data X to pass through. So what's happening in state B, I1 is on, E1 is known to be transparent or inactive. So instead of my clamp data getting passed over here, my X is getting propagated from I2 to output. So this can cause an electrical error on both the isolation gate and the sink. The second scenario is here in the other state table in state B when I'm going from on to on domain, but my isolation cell is active and it is getting the instead of getting my true data value, my active or clamp data value is getting propagated. So here in this check, what we do, we pass on these design constraints in the isolation in the static check and check for any violation coming with respect to allow or block. So if either one of them is true, like if X is getting propagated or data is getting blocked, then we assign correct isolation signals with supply values corresponding to the data signal. So the issues which we faced were like X was getting propagated and which could have resulted in silicon bugs. So we captured such scenarios with the ISO consideration in static checks and avoided any silicon failures. The second challenge was regarding the isolation strategies with camp value mismatch. Isolation strategies are placed while we are moving from off to on domains. At times, we may encounter some situations where the data is already tied to a constant value. So, at these instances, the clamp value associated with isolation strategies should match with the constant tied data input. So, here we got the clamp value mismatch errors. The other scenario which we took care while writing the isolation strategy is the mapping of the cell associated with the clamp value. So there may be a mistake while we are using or an and type of isolation cell and we are getting associated it with 0 or 1. So if I'm using an OR cell and getting a clamp value associated with 0, or if I'm using an AND cell and getting it associated with clamp value 1, then in that case also there will be a clamp value mismatch and it can cause a high current condition producing unpredictable behavior. So here also we ran the low power static checks and we checked for any violation with coming with respect to clamp value mismatch. So in either of the cases, like when my data value was tied to a constant and the isolation cell was associated to a different clamp value as compared to the input died constant value, or if the mapping of the isolation cell was different with respect to the clamp value associated, we corrected all both the errors and then associated the correct isolation cell with the correct clamp value. The third challenge was regarding the pass state table consistency checks between the SOC and hard IPs. PST or pass state tables defines the supply crossing relationships between each supply net in the design as defined by IEEE UPF specification. It also establishes the relationship among the supply nets. They are the golden reference for low power static verification tool and hence accuracy and consistency of PSTs across all hierarchies of the design is the key to delivering a structurally and functionally clean design. SOC power architecture dictates a top level supply crossing specification based on power sequencing and supply crossing interactions. IPs also define a PST in their UPF that define the supply crossing relationships defined by the IP architecture for the specific supplies that exist in the IP. So if there is a mismatch between the IP and SOC supply crossing assumptions, then it can be a potential functional or reliability issue. In case of soft IPs or standard IPs, the internals are exposed to low power static verification tool in SOC. So this ensures we check for any missing isolation and level shifter in the IP design based on SOC power crossing assumptions. But in the case of hard IPs or analog IPs, the internals are black boxed for low power static verification, and hence the SOC is agnostic to the HIP power crossing assumptions and the implementation of isolation and level shifter in the HIP designs. If the hard IP crossing assumptions are different from that of SOC, then this could be a potential bug in silicon at SOC. So such functional issues could be caught by functional validation, but it is limited to coverage. Reliability issues will never be caught. So this check basically covers the methodology gap by comparing the hard IP PST assumptions against the SOC power crossing assumptions and is useful for future generation of products. So the assumption is that the hard IPs verify the internal crossing using the top level PSTs in their UPF. So what we have done here, we have run a custom script for checking the PST consistency. We check for any inconsistency coming from the PST or between SOC and HIP. So if there was any level shifter which was required at SOC level but it does not exist at IP level, similar if there was any isolation which was required at SOC level but it was not existing at the IP level. So we checked for all these type of issues which were reported by the custom script, and then we took these feedbacks and gave it to the IP owners. If there was any modifications which they have to do, they came up with the next version of the IPs, and then they gave their IPs to release. So the issues, yeah, so these issues were captured while doing this PST past state table consistency checks, and we got the rightly configured hips or IPs through this check. The other was like early bug fixes with the synthesized netlist. So we have fixed issues by performing low pass static checks on basic synthesized netlist so that we can catch issues before ST. We ran static checks on UPF created post synthesis. So this is basically a vanilla synthesis having only timing constraints and power constraints information. There's nothing related to floor planning or PNR. So this has helped in reducing cycle time of SOC as any violation which would have been captured post synthesis got caught earlier. We also checked for the cells getting correctly mapped to proper level shifter and isolation cells through the static checks. So we ran the static checks on a basic synthesized netlist, like which was having only the timing and design constraints. And while running on that UPF, we checked for the reports. So if there were two basic scenarios which we encountered, like first of all the correct mapping of the because the mapped cells were there in the synthesized netlist now, and some of the times we observed like there were errors related to the UPF net name changes. The net names which were previously in RTL got prefixed or suffixed during the synthesis, after synthesis. So at times we have got some waivers from the designers for the RTL netlist. So we incorporated those waivers or we modified them as per the synthesized netlist name, and then we also passed on those waivers to the SD so that they can use that case as is. And sometimes we have to fix the issues which were reported after synthesis but were not reported earlier in the RTL based netlist. So all these violations were captured beforehand and thus reduce the cycle time at SOC. Anyways, and reduce our project cycle time also, because eventually they have to come after the feedback from SD or structural design team. So we have done it at our end on the basic synthesized netlist. The other point was like addressing unintended redundant isolation strategies causing the functional failures. So while integrating IPs at SOC, multiple third-party IPs come into existence, which comes with their multiple power levels, power domains, and their respective isolation and level shifter strategies. These issues basically come when we are using the third-party IPs or when we are outsourcing the IPs from any other vendors and all. So however, at SOC's power supplies are significantly different, and at times we have shorted two or multiple supplies to one of the IPs. So the strategies like isolation or level shifter, which were already existing at IP level, become redundant at the SOC level because now their two or multiple power supplies have become our one supply. So we had potential functional failure due to redundant isolation strategies getting placed between AON to AON, blocking the functional data due to clamp value. So for identifying such issues, as represented here also, we have a check at static level, which can show if the data is getting blocked or getting passed without any data corruption. So after identification of such issues with the help of static check, we took care of the following points. First of all, we cross-checked design functionality for redundant level shifter strategies and if they were having the same voltages. And then in such cases, we can ignore them or provide the waiver for them. Second, we checked for the isolation strategies if we saw the data signal which was getting propagated was not getting blocked. So if it is not getting blocked, then we thought, okay, anyways, our data is getting passed whatever we desire. So we then kept as is the redundant isolation strategies, thereby assuring that we are having the correct isolation enable signals or control signals in those isolation strategies. So thus, by taking care of these, we avoided any silicon failures while integrating third-party IPs at SoC level and avoiding any fatal scenarios. So we integrated the IPs and then at the SOC we ran the static check. We then checked for any violation with respect to the redundant strategies, any redundant level shifter or any redundant isolation strategies. In isolation strategies, we especially took care if their data is getting blocked. Otherwise, if the enable is rightly associated, then we thought okay, it will be fine. With this we assigned the correct isolation strategy with the correct data and checked for the design strategy if the path will be active or not. So the advantage with this was like we functionally or we reduced all the potential functional failures coming through in the silicon, which would have come in the silicon afterwards because of these redundant isolation strategies. So other one was like machine learning root cause analysis techniques. As we know, the design complexities are continuing to grow exponentially. This has increased the volume of static check reports in huge number of violations depending on design behavior. Manually debugging the violation is challenging, time consuming, and requires expertise and domain knowledge. So we have taken advantage of artificial intelligence based debug techniques for clustering the static check violations into specific groups known as clusters. These clusters or smart groups are based on grouping the violations which have the same characteristics. After the group creation, the static check performs RC algorithm and tries to club root cause of the specific cluster effect violations together and generates a RCA based cluster. This is done by unsupervised machine learning algorithm. At the end of this process, we get debug clusters with a cause violation. When we fix the cause violation, the effect violations automatically get impacted and we have reduced the number of violations to a great extent. We also get the priority or the rank of the cluster which needs to be fixed first, which eventually improves the overall debug productivity. So what we did, like while running the static checks, we enabled that with MLRCA settings. Then we checked for the reports having the debug clusters created. So instead of the normal reports, we had the cluster reports present, but which it was having a specific debug prefix with the reports, and then we looked for the rank or the priority of the cluster. Each cluster was having its own rank or priority. So whatever rank was the lowest or where the priority has the highest priority, we fixed that rank first. Then there was also the root cause mentioned in the specified cluster. So each cluster was having the root cause also. So when we fix one of the cluster, it was having an impact on many of multiple violations. So fixing just one cluster was resulted into many violations reduction, and there was no need to fix the violations one by one, thereby or it can be fixed in groups because those clusters were based on that respective. So eventually, it reduced a huge number of tags to review and fix. And if we see like in numbers, there was 90% reduction in the number of tags to review. We just reviewed the clusters created at the SOC level, and yeah, basically we can say it was a great achievement or great efficient way of debugging the violations reports. Future research in conclusion. In this paper, we have shown the challenges we faced while doing the low pass silicon sign off at SOC level. We have analyzed the scenarios which can possibly resulted in silicon failure. Following are the key takeaways of the paper. With the mentioned tips, we have increased the efficiency of verification to a great extent. We captured many issues which have been resulted into silicon bugs later. We have given the feedback to the IP teams regarding the PSD coverage issues and UPF constructs, thereby maintaining perfection at IP level as well. The application of machine learning root cause analysis techniques greatly reduced our time in debugging the scenarios and concluding the violations. While running the static checks at light synthesized netlist or vanilla synthesized netlist, it helped us in reducing the feedback coming from the backend team and going into the loop for debug. These techniques help to capture the bugs early in the cycle and hence reduce the project cycle time. We recommend these tips and tricks to be followed while doing the low power verification. Further research is also required to completely automate these techniques in a streamlined manner so that while running as a single static tool, we can capture all the possible cases. In addition, further research is also required on the exhaustive dynamic verification process so that we may not miss out any possible cases coming at silicon. So there were some references which we took help from while debugging or while looking into the challenges which we are facing at the SOC level. They are listed as follows. Thank you.